Hi, everybody. Sorry, I'm trying to reach that back. This is Mr. Rickman, working from home. So I'm on the second page of the notes on set 43, and we're going to do a little more practice of infinite rectangles, okay? So here we go. So I know it says you try, but let's review here. The idea, first of all, is that you set up the area function, or you create an area function. We'll take the limit later. For now, let's focus on that. We start from 1 to the last rectangle. First, the base. Remember, base is delta x, and it comes from the total region divided into n rectangles. So in this case, it's 3 over n. Next, when we multiply by the heights of right rectangles, you talk about where you're starting from and then how many deltas you've gone over. So for example, x1 is 0 plus 1, 3 over n. x2 is 0 plus 2, 3 over n's. So f is, or the heights are f of I, 3 over n's. That says 3 over n. All right. Now you're going to get more specific. You're going to use your actual function. So the 3 over n can stay. And the function is to take whatever you put in and simply square it. At this point, I think I'll just use I, 3 over n's, and blow off the 0. Yeah? All right. Now, we want to clean it up and move all the n stuff out front. So if I take that guy and that 3 over n squared out, then I'd get 27 over n cubed. And what's left inside to count is I squared. Now, again, take a pause to think, what does that symbol mean? It means 1 squared plus 2 squared plus 3 squared plus so on. Well, that's this guy here. There is a formula for adding a bunch of squares ending in n. It's that one. It's the longest one, so we're going to substitute in that formula for adding squares. Again, I'll give you those formulas. You don't have to memorize them. All right, cool. Now there's a formula that finds area estimates using rectangles when you're given any number of rectangles. So if you wanted to estimate the area under x squared from 0 to 3 with one rectangle, I could plug n equal 1 in, and whatever I get out, that would be the same as using one rectangle. 10 rectangles, and so on. The idea for us, though, is we want to take the limit as n goes to infinity of that formula. Now, I typically just take the limit of that a sub n function so I don't have to get so much, I have to write all that stuff again because I'm lazy, all right? It's right above me, so I should be able to take the limit mentally. Now, remember for end behavior, which is the kind of limit you do when you have an infinite limit, you focus on the greatest power in top and the greatest power in bottom. Now, if you're thinking, can I do a lot of canceling? Sure, you can do a lot of canceling, and if you want to, go for it. Me, I just look at the lead terms. The top would be 27 n to the third if I distributed out all the lead terms. That's third. Still getting good at this. The denominator is 6n cubed. If I then took that as n, all the other little stuff I wouldn't worry about. All the other stuff then goes away, and as n gets infinitely large, it just reduces to 27.6 4, 9 halves. That is the exact area. All right. Now then, let's say we do a little more complicated work inside. This one's harder because we have a sum and it requires you to do a little bit of summation notation splitting into 2 sigmas. So write that down for your notes. 2 terms. We're going to split into 2 sigmas later. You'll see. All right. So let's start by writing the summation notation. See how you're doing. Will you give that a go? All right, I hope that's how you started. Then, would you know what to do next without me? And I hope you're saying, all right, now I use the function. Now this is where it gets a little gross. I'm going to do the shell of the function. The function says 3 blank squared plus 1. And then in that blank, I'm going to put 3 over n I. All right, now here's where it starts to get different than the previous. If I distribute, then I would get a 3 over n, a 3 over n squared. So I'd get 4 3s, that's 81 n cubed times I squared. And then I would just get a 3 over n, right? Now you want to isolate. So I'm going to split this into 2 sums. The 81 n cubed out front of I squared and 3n out front of, I guess I'll just call it the ones. All right, now the first one's starting to look familiar. I'm ready for a formula. I can say that's n times n plus 1 times 2n plus 1 over 6 using the formula box above. The second one requires you to either use a formula or use your noggin here. This guy, let's go to blue. This guy really means a whole bunch of ones added. So when I equal 1, you put in a 1. When I equals 2, you put in a 1. When I equals 3, you put in a 1. And so you add a bunch of ones. The question is how many? Well, you're going to add n ones. Now, if you do 1 n times, it comes out to be just n. All right. Now, we're going to take our infinite limit of our a function. If we do that, the top of the first fraction is 81 times n times 2n. So 81 times 2 n cubed over 6n cubed. The n cubes would drop out and it would just approach 81 over 2 or times 2 over 6, yeah? The second one, obviously that approaches 3. Cleaning that up just a little bit, I get 27 plus 3. The area is 30. So that's the idea of splitting a sum, right, into two summations. Okay. Now I need to... Darn it. So here's the problem. I need to get to the next page, and I don't. And I cannot. Okay. So you try this one. It's on the next page. Okay. I believe the answer is going to be 54, but let's see. So first step, did you find the delta x? It's 3 over n. And find the heights at, which are 0 plus 3 over ni. This is the third one in a row we've done 3 over n. I should have mixed it up. Right rectangles. Okay, so the function involves 2. I'm going to put an x there. And 3, and I'm going to put an x there. So there's 2 different x places I'm going to need to put in this time. And so I'm going to have 2 different 3 over n i's. Okay, so cleanup time. I'm going to do this a little quicker this time, which is what you're going to eventually get to. So if I distributed this out, I would have 3 over n 4 times and a 2. Right? And inside, I would have a I cubed. Okay, I pulled that out, and that out. Cool. In the next one, I would have a 3 over n to pull out there, and another 3 over n, and a 3. So I'd have a 3 and 3 over n squared, and inside I'd have an I. How'd that go? All right, so formula-wise, what do I got here? 3 to the 4th is 81, so 162. If you want, you can keep it out, whichever you prefer. 9 to the 4th. The formula for cubing is n times n plus 1 all over 2 all squared plus, what is that, 27 over n squared. And the formula for i's is n times n plus 1 over 2. Again, a lot of students want to clean up the ends, and that's fine. I just look right above in the step above for my infinite limit. When I take the infinite limit, this guy would be 162 times n squared, so 162 n to the 4th and stuff over 2n to the fourth. So that one seems like 81. The second looks like 27n squared and stuff over 2n squared. So that seems like 27 over 2. So I think my answer was incorrect. It's not 4. Nope, that's where I was wrong. So this 2 was squared. So that was over 4. So that's 81 over 2. I apologize. 81 over 2 plus 27 over 2 is 108 over 2, which is 54. I should have trusted my calculus. All right. So 54 is the perfect area under that curve. That was a little rougher, but I hope you're also getting better. All right, last example. All of these have been easier because they've started at 0. When they don't start at 0, that makes for a little grosser type, and then we'll be done. All right. So if we find the area under, then what's the base? This time I hope you're saying delta x is 3 minus 1 over n, or 2 over n. The function then, when we draw our heights, we're starting at 1, and so the first x at which you draw a right height would be starting at 1 and adding a 2 over n once. The second x would be starting at 1 and doing 2 over n twice. So the ith x would be starting at 1 and adding 2 over n I times. Now if we plug in the function for this problem, then it's 2 over n, and I put the shell of the function down. It's 2 blank, leave a big blank now because it's a sum squared plus 1. In that blank goes 1 plus 2 over n I times. Oy, yoy. Man, this will be as gross as you'll see. All right, so if I want to expand this, I need to go back to red. If I want to expand this and pull out common factors, first I need to do the square. So that would be when you square 1 plus 2 over n I times, please, I remind you, don't think that you just square each term. You should know better than that by now. You get 1 plus 4 over n I plus 4 over n I plus 4 over n squared I squared. Jeez Louise. So 1 plus 8 over n I plus 4 over n squared I squared plus the one that was out there before. Okie dokie. When you get good at these, you might combine a step or two, but I'm going to go slow. So when you distribute and combine like terms, I get a 2, but I also have a constant out there, so I'm going to get a 3 plus 16 over n I plus 8 over n squared I squared. Finally, we're ready for our splitting our sums. All right, so I'm going to have a 2 over n outside 3 then I'm going to have a 2 over n and a 16 over n. So a 32 n squared I, and then a 2 over n times an 8 over n squared. So a 16 over n cubed I squared. Let's see, do I have room for one more line? Yes, okay, cool. All right, so formula time, here we go. 2 over n, and when I add 3 to itself n times, it would be n times 3. I'm adding 3 plus 3 plus 3, so it would be just 3 times however many I had. The next one, formula is n times n plus 1 over 2. And the last is n times n plus 1 times 2n plus 1 over 6. All right, and that's a cube. Okie dokie. So, yikes. Roughly then, this is 6 plus, when I'm just kind of trying to prep for taking my limit, this next one would be 32n squared and stuff over 2n squared. And then the next one would be 16 times n times n times 2n, so 32n cubed over 6n cubed. So that when I take the limit by n behavior, I'd get 6 plus 16 plus 16 thirds. So what is that? 18 plus 48, 66. I'm getting 82 thirds, I believe. I'm going to check that again. 6 times 3 is 18 over 3. 16 is 48 over 3. 18 and 48 is 66. 66 plus 16 is 82 over 3. There you go. All right. I believe that is it. And now, hopefully, you should be able to do the homework. The homework is due tomorrow. Have a great day.